So this talk is about some set size finite sets of integers, and it includes results I proved in the last or two. So there's a degree of unreliability to this. But the talk starts when Bryant asked me about the following statement of Dish and Semretti, which was in their famous paper on the sum product conjecture. Said if you take an integer t between 2 minus 1 and n squared plus n2, they wrote it's easy to see that one can find a sequence of exactly integers so that there should be exactly distinct integers of the form aij. In other words, if you take the set A consisting of these n integer twofold set will have t elements, and t can be any number between this lower bound and upper bound. And Kevin asked me could prove it, which I did, and it led. So it made me thinking about this question of the sizes of some sets, and so the general question is the following. I'll look at the range of sizes or range of cardinalities of all H-fold sum set of sets of size k in an abelian group. Well, we'll see abelian group or group just to be integers, but these results extend. If you look at all sets of integers of size k, and their H-fold sum sets, how big can those sets be?
Okay, Mel, sorry to interrupt. We're still getting this this echo. It's like your sound is jumping around out of order. We're missing some words and hearing some words twice.
Well, that might improve the clarity of the talk, but I have no idea how to remedy this. I have one. Let me try one other thing.
It may be that people aren't muted, and someone's computer is hearing Mel and then also sending everyone else Mel. So maybe people muting might help. Not Mel muting, but others.
Right. Is there still an echo?
Yeah,
Can't tell if
the
there's an
echo
echo
is
or not.
Yeah.
Give us some pattern, Mel, so we can tell if it's fixed.
I am chit-chatting.
Maybe your computer is running something processor heavy and is having trouble dealing with the sound, something in the background.
I don't know. Let me try another computer. No, and there still is an echo right now.
No echo.
No echo.
Seems good. Seems good right now. Well, again, I think.
We'll see how long it lasts. Sorry. So, So in general, if you take the integers and if you take a set of k integers and look at the h-fold sums, the minimum as size it will be h minus h plus 1, and the maximum size will just be the combinatorial upper bound, which will be k h minus 1 choose h. So this is a statement that Erdős and Emeretti made in their paper, that if you take it into t between 2k minus 1 and k plus 1 choose 2, there always exists a set of integers of size k whose sumset is size t. So in particular, the set of sumset size is an interval of consecutive integers. There's no gap. And then, so I'm not aware of any papers that look at this question of the range of sumset sizes of a finite set of integers. So this is for two-fold sums, and it's natural to look at h-fold sums. So you look at all h-fold sumsets of sets of k-integers, and there's a lower bound and an upper bound. And the question is, just as the case of two summends, when you have three or more summends, do you get this whole interval of consecutive integers? And the answer, sorry, before I say that, let me go back. So I'm just repeating the theorem I wrote, but with one additional bit of information. So not only is there a set of size k, some set that has size t, but in fact, you can always choose in the interval between 0 and 2 to the k minus 1. So this is an answer to the following question, which is, if you know whether there is a h-fold sumset, a set of size k of cardinal exactly t, is this a finite problem? That is, can you solve this problem with finite amount of computation? This is not to ask yet whether this is polynomial type or exponential type or super exponential, but simply, is there a finite computation you do that will answer this question? So in the case of two-fold sums, here's the answer to the question. If you want to find a set whose two-fold sumset has t, you only have to look at subsets of the interval from 0 to 2 to the k minus 1. So only finitely many subsets of size k in that interval. You look at them all, it may take a while, but eventually either the sun burns out or your computer burns out, you find the answer. But it's a finite computation. Okay. Now, in general, if you're looking at h-fold sumset, for h greater than or equal to 3, the lower bound for the size of the sumset is hk minus h1. And arithmetic progression will also give you this many elements. But for h greater than or equal to 3, the next larger number is never the size of a sumset. So I mentioned in my talk 2 weeks ago, this is really what makes this subject for me a little bit interesting, more interesting than it might otherwise be. For h greater or equal to 3, the range of sizes of sumsets is not an interval. There are missing sumset sizes. There are gaps. And the next largest number, hk minus plus 2, never the size of a subset. Okay. Now, so this raises a lot of questions. The simplest is, what are the ranges of sumset sizes for sets of size a and a greater than or equal to 3? And as far as I know, this is an unsolved problem. Unsolved means I don't know the solution. I don't I haven't found anyone who's this in the mathematical literature. It certainly doesn't mean that in the universe it's really unsolved, but just don't know an answer. But the new question, which I did talk about so much 2 weeks ago, is the following. So this R of HK, this means this is the set of all sizes. This range of cardinalities, this of all sizes of H-fold sets of sets of K integers. Suppose T, you know T is in this set somehow. However you know T is in the set. That means there exists a set A sub T. You can always normalize if you like. So the smallest element is 0. And the H-fold set has T element. Now, if you look at all of the T's, all the set sizes, for each such T, the set at this property, HAT is T element. So if you look at the collection of all these ATs where the small element is 0, and you take the maximum of all the largest sets in these sets, there does exist interval capital N such that every subset size is the subset of a set of K integers between 0 and N. And then the question is, so such an exists. The question is it computable? Can you find it? So can you find an integer N such that for every T, which is a subset size of a set of K integers, when you look at H-fold sums, can you compute number N such that your set is contained in this interval? So solving this problem of finding all T's and all sets and set with that property is a finite problem, right? That is, if you start your computer, eventually it will stop, right? So that you want to guess? My guess would be just the way for twofold sums. All sets were contained in an interval between 0 and 2 to the K. It might be in this case, all sets are contained. There's always a set in an interval from 0 to H to the K. But I don't know what the answer is. So that is, if you like, old news, and new news is this two of this talk, which you might call inverse problems for some sizes. So you take A to be a finite set of integers. You look at the H-fold sum and its cardinality. So what you might call a direct problem for some sizes is have the sequence. You have your set at A. You look at the H-fold set and how many elements are in it. So you get this infinite sequence of positive integers, steadily increasing sequence of positive integers, and your sequence A, your set A, determines the sequence. And this is, I apologize for the question marks, but from some point on, this is the basic, from some point on that is for sufficiently large H, this is simply an arithmetic progression. So the H-fold some set sizes increase by a fixed amount as you go from H plus 1 to H plus 2. And if you've normalized that, so the maximum element is A, the smallest element is 0, and you've divided by the greatest common divisor of the elements, so the elements of the set are relatively prime. Then as you go H plus 1, cardinality of the sums increases by exactly A. That is, difference in the arithmetic progression, which is the maximum amount of the set at A. So this is what you might call a direct problem. And there's a tradition. Oh, okay, so all right. Let me just make one observation. The size of a subset is defined in variant. So we say A and B of integers are finally equivalent if they're rational numbers lambda 2, such that B is lambda times A plus mu. So 1, 4, and 0 are finally equivalent. Also, if you take the symmetric image set instead, if you have the set A and you replace it by the maximum minus the elements, where is that at? Yeah. No, it's not. But replacing, if you have a set A between 0 and 10, you replace all the elements by 10 minus little a. That's also an affine image. And if A and B are affinely equivalent sets, then the size of the H-fold M set, some set, is the same for A and B. So some set size is an affine in okay. This is the remark I made a few minutes ago. If you have a finite set of integers, smallest element 0, largest element A, and the integers that are relatively prime, then there's some fixed number delta such that from some point on, the number of elements in the sum set is HA minus delta. So it's just some arithmetic progression. It's a little bit more complicated to understand the size of the sum sets. For small A, but after a very short time, things become extremely stable. Okay. So it is natural in the perverse world that mathematicians live in, it's not natural to consider or to ask some inverse questions of sequences of size of some set of non-empty finite sets of integers. For example, if you have a sequence of positive integers, and you know that the eighth term is the size of the H-fold subset of a set A, to what extent does that determine M and A, right? So this is the analog, if you like, of like the Feynman question. If you have a set of K integers, a sum set is small, that is constant times K, what can you say about the structure of the set A? So here the question is, if you have a finite set of integers, you know the sizes of always some set, well, what does that say about A? So if A and B are affinely equivalent, then the sequence of some set sizes is the same. So the question is, what are the relations between sequences of some set sizes for affinely inequivalent sets of integers of the same size? For example, can you find affinely inequivalent sets of integers for which the sequence of some set sizes is the same? Or you could ask for more exotic behavior. For example, can you find two finite sets of integers, and if you look at the first sum set size, and you sum number H1 1,000, the sets have exactly the size for H up to 1,000, but after then they're different. Right? So I answer some of these questions. And the way to think of this is the following. To the extent that this is a new series of questions, you ask all the questions, however they may seem, see which ones you can answer, and then those you can't answer are the interesting ones. Here's a little theorem. So for k equal 1 and k equal 2, k is the cardinality of the set. If you have a set with one element, all the sum sets have one element. If you have a set with two elements, the eightfold sum set will always have exactly each plus one elements. But of course, all two subsets are affine equivalent. So this is only interesting for a side of the set at least these three. And there do exist affinely equivalent sets A and B that have the same size, and all of their subsets have the same size. And the proof is just by explicitly calculating examples for all k. So for example, you take k equal 3. Here are two sets with 3 elements. Here are their twofold sumsets. Here are their threefold sumsets. Here are their fourfold sumsets. This is all I must say paper and so works. So hopefully I didn't leave anything out. I count up the number of elements in these sets. The twofold sumsets have 6 elements. The fold sumsets have 10. The fourfold sumsets have 15. And for 5 and greater fold sumsets, you have CA and DA, CB and DB. This plus this have 15 elements. This and the other have 15 elements. And by my favorite theorem about structure of H-fold sums, H greater than or equal to 5, HA is the set, H is this set, and they have exactly all H, 7H minus 14 elements. So here we have 2 3-element affinely inequivalent sets for which the sequence of some set sizes is the same. For 4 sets, here are 2 affinely inequivalent sets, and fold some sets all have 6H minus 3 elements for H greater than or equal to 2. So if I did this right, the twofold sumset has 9 elements. Hope so. For K greater than or equal to 5, here are 2 families of sets. A is 0, 3, 5, 6 or something, and this means it is an interval of integers, so you can make this as long as you like. Here's the set plus another interval of integers. And for H greater than or equal to 2, these sets have exactly the same number of elements. They all have, these sets have K elements. This is the same. So in this business, a useful experimental class of finites to look at are sets that are the union of finite interval of integers plus one additional element. So here's a very nice class of sets. Take the interval of integers from 0 to L, and then you tack on a bigger number W. W is an integer greater than or equal to L plus 1. Okay. So we have this set, and J0 is this odd number. This is the greatest integer in H plus 1 minus WL. And you can calculate exactly the size of the H-fold sumset. If W is at most HL, then the H-fold sumset is given by this. And if W is bigger than HL plus 1, then the H-fold sumset is given by this. So once you have this data, it's useful for constructing or trying to answer questions. So I had shown minutes ago that you have 2 sets that are affinely equivalent, but the 8 sumsets have the same number of elements for all 8, from 1 to infinity. You could ask, if you pick some number A at least 3, and any positive integer n, whether you find 2 sets A and B that have exactly K elements, and their sumset size agree up to H1, but once you get past 1, the H-fold sum of A is strictly bigger than the H sum of B. So you look at these sets for a certain amount of time, they had the sum sets. I mean, you think of like every second you compute another sum set. For a long time, these two sequences of numbers are the same, and then they diverge, and then one is growing faster than another. So some guys exist, and yeah, sorry, let me go. So I'm not giving any examples or proofs, but such guys exist. In due course, as I always say, something appears in the archive, but so you can always do this. Now, there's another kind of question you can ask. So you imagine you have two sets A and B, and every second you compute the next higher sum set. So you look at how big are A and B, how big are the twofold sum sets 2A and 2B, 3A and 3, 4A and 4B, and so on. And you might ask, can it be the case? Can you find sets A and B up to a certain point 1, say the h-fold sum set of A is bigger than the h-fold sum set of B, but then it reverses. And beyond that point, the h-fold sum set of B is bigger than the h-fold sum set of A. So here's an example of something like that. It's very easy to construct equals, but it's interesting to record the phenomenon. Here I have two sets A, B. This has 5 elements. This has 4 elements. Here's 2 and 2B. So this one is smaller, is bigger than this. Here, these sum sets both have something is missing there. These sum sets actually both have 9 elements. But now we get to the threefold sum set. The threefold set of B has strictly more elements than the threefold sum set of A. So you get this reversal. And it's actually for these special sets that I like, which consists of an interval together with a large element. I mean, I actually did some calculation of as you go down, this is the number W. So W has to be at least 5, 6, 7, 8, 9, and so on. And going across the twofold sum set, threefold sum fold sum set. So as you look across this set, you can see the increase in the sum set sizes. All right. You go down, looking at the increase in the sum set sizes for a fixed number of summands, but where W is increasing. And what you notice is, of course, eventually it becomes constant. When W is large enough, it makes no difference what this is. Interesting patterns of numbers that you see in a table like this. So let me just mention a couple of open bumps. So you can construct sets A where the H-fold sum set, H1-fold sum set of A is bigger than the H1-fold subset of B, but then it reverses for some H2 later on, where this sum set is smaller. And this is just the example I gave a moment ago. So, problem. If you have, this is actually, I think, an interesting problem. If you have two sets of integers, the same cardinality, the same size, suppose that sum H1, the H-fold sum set of A, is bigger than the H-fold sum set of B. Does that pattern persist? Is it the case HA is greater than HB in size for all H bigger than 1? in what I might call a counterexample to this, this A and B had different sizes. One had 4 elements, the other had 5 elements. When you have two sets of the same size, if at some point for some H or some H1, H1A is bigger than H2B in cardinality, does that persist for all H for H1? Right, right. The real problem is that A and B be non-empty finite sets of integers with the cardinality A equals the cardinality of B. Sorry, I left something out, I think. So this is essentially the same problem that I just meant. But this is really another problem. And I think you can look at analogous problems for restricted sumsets where you get sums of distinct elements. There are analogous problems for linear forms. There are interesting problems when you deal with the finite sets of lattice points. But let me just close by emphasizing what I think are two really very interesting open problems. The first one is a finite computation to determine if there is a sumset HA of size T for ME for subset A with K elements. And I mean, is that a finite calculation? I had asked earlier, this is a polynomial time calculation. I don't even know, though, that exponential time. It could say that for
You're
given...
not on the right slide, yes?
Sorry?
This is not on the slide, yes?
It's not on the slide.
Okay.
It was on the earlier slide, but I just wanted to emphasize it because I think it's really quite interesting. Can you find number n such that if there exists a set of K elements whose H-fold set is T, then you can find such a set interval from 0 to 1. So that means that's an exponential time calculation. It's not even polynomial time, but at least it's finite calculation. And I don't know if such a thing exists. And the second problem is just the problem I mentioned right here. If you have two sets A and B of the same size, and if one H-fold sumset is bigger than the other H-fold sumset, does that persist forever? That is, if H1A is bigger than H1B, is HA always bigger than HB? It can never reverse. And this I would think there is certainly yes, but I don't know. And that, as it turns out, is all I wanted to say. These inverse problems.
Can I ask you about the last two problems?
Yes.
It looked like the second one and the first one were kind of similar.
They were the same. I was putting these slides together.
Why were there two then? Is that like the echo we're hearing?
Yes, it has infected the video as well as audio. So among this very well-educated erudite group of listeners, does anyone know of anyone who's ever looked into this question of the range of size of sumsets? I mean, there's like a huge literature. If the sumset is small, then you have infinite amount of work describing the sumset and at what point thing again. But that's just for very small sizes of sumsets. But I'm not aware of anyone looked at the range of all sumset sizes of a set of K integers. And as I said 2 weeks ago, if you can prove this is a polynomial problem and is also incomplete, you will win $1 million.
What is it? First of all, there's a great problems there. Lots of nice problems.
All right, but what my question is whether you've
Problem
seen
winning $1 million is going to become problematic in about 4 years.
4 years. That's
4 years.
that's when you think AI will solve the problem. What?
No, I think in 4 years you'll need $1 million to make a phone call.
Oh, okay. Okay.
So, Mel, do you have a guess for what like maybe the best value of n would be? I mean,
Well, I
it seems like it's
said
plausible that it's t,
two.
right?
It's 2 to the k, and so maybe for h fold sums, it's h to the k. There's no reason why that should be. It's just if you don't have much imagination, you place 2 by h, and you get an h to the.
But even the number 2 to the k isn't best possible. Right?
You know,
It seems plausible that it could be like
problem.
so
2t even.
so the worldness of mathematicians who want to get the best possible results, and mathematicians who wanted a result. So I'm a group of people who want to get a result. Like Henrik is on. He might appreciate this comment. Like for the Dirichlet-Weiser problem, you have some main term plus some exponent, like some x to something. And if you make that something smaller, you've set the new world record and get a lot of applause. But you still haven't solved the problem. You just made the exponent smaller. So for me, I've never been that excited by such things. I've worked some sometimes, but I just wanted to know, was there an explicit number n I could find where every set that t every
I like
so it's that for every t between the upper and lower bounds, there was a set between 0 and 2 to the k minus 1 with that sum set size. And I wasn't trying to optimize it. I just wanted to know if I could compare. We know it exists because they're a finite collection of sets and they have the largest element in their union. So we know such a thing exists. The question is, can you find it? So I was not trying to optimize that in any way. I found a number and I was overjoyed, and I said, "Good. Now, what about fold sumsets?" And I don't know the answer, nor do I know what the range of possible sumsets of a 3-element set of integers. Right? That's a very easily problem.
Wait, can you repeat that? The echo is that sounded interesting, but the echo garbled it a little bit. I want to make sure.
I said, no one, as far as I know, sorry, let me say 2 things. First, as far as I know, I'm the only person ever thought about this. So if I don't know the answer, one would conclude that knows the answer. So that's a hard problem. It just means I haven't solved it. And now telling people, well, maybe some solve it. But you look at all sets of 3 integers. All right. Sorry, forget that. If you look at
Threefold sums.
if you look at all sets of k integers and you look at their threefold sums, what are the ranges of the sum sets sizes that you get? So solve that problem just for threefold sums.
So you know there's a gap right at the beginning. And the question is it gappy or is it just an interval from some point on?
Right. So I did whatever idiot does. I started to compute this for small k. And at some point, it becomes a little bit laborious. But I have a list of, written down the paper that's, or the, my write-up of all this stuff as I write it. That for small k, that's the only gap, that initial gap. Right? Now, I would have no reason to believe one way or the other that's the only number that's missing when you let K be the number of atoms in the universe, right? I mean, who knows? I don't. But but that's like a natural, simple problem to ask, and so I owe this. I should emphasize to Kevin, who asked me this initial question, the comment in the editor Samaretti paper. And there are a lot more questions you can ask. There's you know, if you get energetic, you can write down, 100 problems, all with have some interest. But if you can't solve the simplest ones, there's who knows?
Mel, have you looked for this question about difference of sizes at sets that have like a big arithmetic progression and then two numbers away?
So,
One and another.
so I started to do some calculations with that. But again, and I far from finished. I've hardly done it. So, but you have to understand, everything I talked about with these verse problems, all stuff that's only a couple days old, a week or less. And I suddenly thought about this question for some reason. Yeah, so it'd be natural to interval. Well, it's actually even a little bit complicated to take a union of two intervals, right? So, and there's some subtleties there that have to be worked out. And what you're suggesting, I think of similar difficulty when you an interval plus a larger number plus an even larger number, and you have to worry about all sorts of interactions, and
Just to see if with these examples there is plausible hope to get this reversal of fortunes behavior.
all right. Yes. I don't. I mean, if you think about this, we communicate online, but you know, life is short, and bumping makes me life is even shorter. But yeah, it really is amazing to me how much one can do. I know a tiny bit of maple, but just knowing a few dozen maple commands, programming, actually 4 or 5 at most maple programming commands, you can actually do a huge amount of calculation. But with these problems, I have a fairly decent, much newer Apple MacBook than the one I'm using right now, which I use Maple, and even some very small calculations. It takes Maple a long time. I mean, I'm sort of sitting there, at the window waiting for an answer to come up. Now I know for any of you who's a serious computer person, everything I'm doing is trivial, but I know because there are people here do major calculations. That you don't expect an answer in 5 minutes. You expect an answer in I don't know how long. But just that little bit of maple is really fantastic. So I have to say, I could ask ChatGPT, but I don't think quite up to the level of this yet.
But it would happily pretend that it is.
ChatGPT is probably already writing math papers.
No, I don't know.
contributing, or you mean like top to bottom?
Well, I think it's hijacked a human to submit them.
Okay,
Just
well,
wait, yeah, just wait when they automatize the journals, acceptance and reviewing policy and everything using AI.
If it does the review, it's already good.
No, but
Yes,
this
we
is
should
an
hire AIs to be referees. That would certainly be a problem to deal with the problem of
Jeff?
getting a good referee.
Jeff, do you remember how long ago that Liska wrote his famous paper predicting the demise of all print journals? Was that like
No.
30 years ago? Hard to tell what's going to happen.
It's. Do you think the state will wither away first?
The state will wither away?
Isn't the state supposed to wither away?
A couple hundred years ago. Long overdue for that. Yes. Yeah. Okay, everyone. We'll break for Christmas, Hanukkah, whatever you might or might not celebrate. And
Thanks for a very nice talk.
thank you for
Those are
tolerating.
they're very stimulating problems, and probably they're worth thinking about.
And you heard it twice because of the echo. So
I'm
thank
still
you.
hearing it.
All right, be well. Happy New Year. See you sometime next.
See you
Thank you.
guys. Thanks for the memorial for Dick Bumby.
Yeah.
Yes, thanks, Mel.
Yes.
Mel, thank you very much. Be well.
Yeah, you too, David.
Thank you very much. Thank you very much.
Happy New Year, everybody.
Happy New Year. Yeah.
The same. Bye.
All right, bye all.